Hello and welcome back to the development of the Feersum Scheme compiler. So in this stream I'm going to try and look at implementing tail calls or proper tail recursion as they're called in the scheme specification. So I'm going to go over what the problem is that they solve, how we can solve them in .NET, and then go and implement them in our compiler. So a tail call solves a problem that's to do with recursive algorithms and stack overflows. So let's start by taking a look at one of our recursive examples that we have at the moment, which is, I can just find it by name, itafact. So in itafact, we have an implementation of the factorial algorithm, which is this implementation here, should be able to compute it using recursion. So it has an accumulator, and it basically always makes what's called a tail recursive call, where the last statement in this method is just a call, so we don't actually have to do anything after it in itafact ack after we call recursively. Now, if we try and calculate the factorial of 24, then we end up factorial of 4, we get 24. If we try and calculate the factorial of 1000, let's try and do this. So we'll do .NET run Feersum is our compiler, and then the arguments we're going to pass is spec itafact. So this will hopefully compile Feersum and then try and compile itafact with it. And now we should be able to do .NET. It's been a while since I've actually used this. So that has computed the factorial of 1000 as being infinite, which is fair enough, really, to be honest. But the key here is that it has actually computed it. If we do something slightly smaller, hopefully it'll... Oh, I need to recompile it. Yes, that needs to be .NET. Yeah, so we get a very big number. So as this number of iterations goes up, the number gets bigger. But if we go to 10,000, we still get infinity. At some point, because of the way that this is working recursively, we'll run out of space in the stack and we'll end up with a stack overflow exception like that. So what this is telling us is that somewhere right at the top here, so far back that I've lost the scroll back, it's saying that we've overflowed the stack at, and then it's saying it was in lambda 1, lambda 0, lambda 1, lambda 0, all the way around to our entry point. So if we have a look at the original source code, so this is lambda 0, this is lambda 1, this is lambda 1, lambda 0. So it's a recursive call inside here. So it's this itafact with accumulator. So we can come up with a slightly more, slightly simpler. So I'm just going to undo all of this so that the tests don't fail for that. If we create a new spec, we can come up with a simplified version of this. So we can say, well, let's do mutual tail recursion. So we say let rec ping, so lambda, takes no arguments, and calls pong. And then we define pong, so lambda, that calls ping. And then we just call either one of them. So if we go and get our compiler up again, no. So we'll compile tail.scm instead. This should tail call until eventually. Yes, I've spelled lambda wrong. Should have picked that up from the syntax highlighting. So here we see the same kind of thing. But in this case, we've got lambda 0, lambda 1, lambda 0, lambda 1. So we're making these mutual tail recalls recursively until we eventually overflow the stack. So what does the scheme specification have to say about this? So implementations are required to be properly tail recursive. Procedure calls that occur in certain syntactic contexts defined below are tail calls. So basically the scheme specification says that if you want to conform, you must support a given set of expressions as being tail calls. So we'll go through what they are in a bit. And effectively what it says is no space is needed for an active tail call. The continuation of the tail call has the same semantics as the continuation pass to the procedure. So this is to do with the way that Scheme models function calls, which is different from the way that we model them in our language, because it's actually we're running on .NET, where functions return values, but the way that function calling works in Scheme is functions are kind of take an implicit continuation, and so rather than the function returning the value, the function calls into the continuation with the result effectively. So a lot of the time you can't tell, and hopefully Feersum will just support as much of the scheme specification that we can without actually getting proper continuations. There's some, I wouldn't call them hacks, creative solutions on the horizon to supporting some of what you can do with continuations. But effectively what this is saying is that we shouldn't allocate extra space. So how do we do that? Let's go and take a look at. So we can imagine that initially our stack looks like, and let's do this in the code window instead of Emacs. So our stack would initially be empty, and then we call ping, and then ping calls pong, so we push it on. So we have like effectively we have all of the locals of ping, which is nothing, and then also the return address, and then get pong on the stack, and then that calls ping, and so on and so forth. So until eventually Stack Overflow. In the non case, would it help if I could spell? Well, not spell, type. So what we want to do with tail recursion is we start off with the stack that contains ping, and then when we get into ping and we call pong, this is the last element in the lambda body, so it should be a tail recursive call. And what we want to do is allocate no space. So what we effectively want to do is have that become, so the stack doesn't change in depth. Whereas let's how would I do this? So let's just try and illustrate how the stack changes over time here. So this would be like this. And then we're back to a ping up there. So we're treating as that like some snip through the stack, and then you get stack overflow. Whereas in this case, what we want to happen is that every single time we just go ping, and then so what's happening is that normally when you make a function call, you push the new function context onto the stack. So every time ping or pong calls each other, you'd end up with an increase in the stack depth. The way that tail call works, or the way that tail call is implemented in .NET, is that we have a special prefix that we can put onto opcodes to say that this call should be a tail call, and then when the .NET VM actually executes it, when the JIT makes the call, we won't use a call instruction, it'll use a jump instruction. So effectively what happens is, instead of pushing something onto the stack and then calling into Pong here, what we do is we would just clear out our current stack frame and then jump to the entry point of the method, which would mean that effectively we've cleared our current frame from the stack, and then whenever Pong returns, it would return to wherever the original call to ping came from. And you can just keep on effectively reusing this same stack slop even when we're not making a call into the same method. So let's go and have a look at what the scheme specification says about the cases where we have to support it. So it says the last expression within a lambda body occurs in a tail context. The same is true for all bodies of case lambda expressions. And so basically tail calling all starts off from where you defined a lambda or a case lambda. We don't support case lambdas yet, so lambdas is all that we care about. So what it says is that when you have a lambda definition, you've got your definition and your expressions. You've got your list of expressions, but then you've also got a tail expression at the end. So what that's effectively saying in the grammar is that the last expression in a lambda body is a tail call. And then we have these various other forms that we need to support. So effectively it's saying if you've got something that's in a tail context, then if it's an if or things like a begin, then we need the last thing that's executed to be also in a tail context. So it's kind of the property of being a tail expression is recursive. So that's what the problem is. That's what tail calls are. And in .NET, let's try and create an example of this in .NET. So how can I do this? Yes. Let's go find this. So we have our program. We can do the ping pong thing that we had before. So we will define a pair of functions. So we say let rec ping, which takes no arguments. All it does is call pong. And then it's also mutually recursive with pong, which takes no arguments and calls ping. And then our entry point is just call ping. And then with any luck, I should be able to .NET build, and this should compile. Nope. Oh yes, because we actually need to call these, because this is the way F# works. So if we try and run this, what we should see, that has overflowed the stack. That's unfortunate. I was hoping it was going to be tail recursive. So I guess, do I need to do configuration release? I guess I do. Yeah. So that is running, and it hasn't crashed. So what we can see from that is that at least if you build it in release mode, F# supports tail recursion. So how does it do it? So well, let's use ilspy, and we will do, it was bin release tail, no, tail, and we will output it as il. Which I think I just need to redirect it. And then let's have a look. So There's a whole bunch of metadata to do with git version, pre-release tag stuff. We don't care about that. Let's go find ping. So here is our program, which we have the two methods, ping and pong, and the main. So main calls ping, ping calls pong. And it looks like the way that the F# compiler has chosen to do this is it just does a branch. Have I broken something? So it's identified that they're mutually tail recursive and it's got rid of it completely. Great. Effectively, what I was trying to get it to do, let's have a look at the debug, because debug might help us here. Nope, debug just doesn't do the optimization. So the F# compiler is either not smart enough or too smart. But effectively, there is an opcode prefix that you can use in .NET, which allows you to make a call tail recursive, and it's called tail. So how are we going to implement this in our compiler? I'm going to start by... So this is kind of to do with when we actually take the bound expression and compile it down into IL. So if we start in compile, I'm going to go to compile expression, emit expression. So emit expression at the moment takes a context and a bound expression to emit. Now, we kind of want to keep track of whether or not we're in a tail context. We could put that in the emit context, but it's not really global state because being in the tail context is specific to this bound expression. So I'm just going to have a tail boolean. And then whenever we recurse, we'll recurse into tail. And now we just need to find all of the places where we recurse. So if we've got a sequence point, we recurse, so that's fine. So we pass on the tail call. So if we are in a tail context and we encounter a sequence point, the sequence points inner expression is in a tail context. If we have a store and it's in a tail context, we can't be in a tail context, so we have to do emit expression context false, because a store is not tail recursive, because we can't just return out of the method because we need to write it somewhere. If we have an if, then we can't easily tail call here. So I'm going to change this to be context false, because the condition of an if definitely can't be. And for the time being, I'm going to ignore tail calls in true or false as well. And then if we want to emit a lambda or quoted, yeah, they're just defining values, so we don't have anything to do there. So now we have to look at all the processes that we've broken, which will be everywhere where we call emit expression. So if we're in a sequence and there's one item in the sequence, then we call emit expression. We need to take the tail here. Tail, we pass on, and if we've got an item in the sequence and this is definitely not the last one, we can't be making a tail call. So we need to have a look at where's emit sequence called. Up here. So pass on there. Whether or not we were in a tail context when we came to a sequence. Emit an application. So an application in our case is a call. So we definitely want to pass on whether or not we're in a tail context here. So let's put tail again, go find where we call it. Pass on whether or not we're in a tail context. So we've got a few emit expressions here. We've got the emit expression for what we're calling, what are we calling it? AP. Applicant. Oh yeah, applicant. So the thing that is being called effectively, the thing that we're applying, and then we've got all of the arguments that we're applying to it. So neither of these can actually emit a tail call because at the end we need to emit this call here as a tail call. So that wants to be false there and false here. And then down here, we were about to call invoke. So what we want to do is say if, and this is the bit where we will actually make a tail call, if tail, then emit opcodes tail. So opcodes tail is the tail prefix. It's not a huge amount of docs there for it, but trust me, it is. And then what else have we got tracking through this error? So emit expression. So this is the case where we're actually emitting a lambda. So if we're emitting a lambda, the scheme specification says that the last expression in a lambda body should be in tail context. In this case, the body of our lambda is just an expression, because if we have more than one element, it will end up being a sequence expression. And we're already handling the last element in a sequence being in tail position. So we can just say true because we want to emit the body in tail position. So now I should be able to build, and I'm just going to find the tail example we had. Nope. Yeah, our source code. We'll just do we need to remind ourselves to clean this test up and commit it. We don't want to actually run the tail recursive stuff yet. So let's run the tests and see what happens. So we've got 2 failures, which is positive. So the failures are that we don't have snapshots for tail, which is good. Let's try and actually run our tail example again then. So if I let's move that down so that we should never see fix me. This should just sit there and endlessly tail recurse. So let's go grab ourselves a shell. Hopefully this is one where we previously did a build. Yes, that's running the tail one. So that's built. And you can see it's there, it's running, it's consuming CPU, this one here, 98% CPU. So it's sitting there and running and being tail recursive. So I'm going to close that. So we can also have a look at IL spy for this. So look at the IL for spec bin tail DLL, and we'll say that it's tail.il. Which is the wrong tail. IL. We wanted one up here. So let's have a look at our program. It's usually easier to read these things from the bottom. So we have lambda1, which is this is going to be Pong, and we have lambda0, which is going to be ping. So what it does is it creates an environment, stores the environment on the stack, sets the slots on the environment, and then it creates an empty array, which are the parameters to the method call, and then it does tail.call. So this is the reason why F# is, this is the reason why .NET isn't overflowing the stack anymore for that program, because that has a tail.call, and down here this also has a tail.call. So say we wanted to stop this from just dying. Let's say we want to start off with giving it a number of iterations, and we knew that 100,000 was enough to overflow the stack before. So we'll say that ping is a lambda that takes a value, and so is Pong. So Pong, let's just pass it straight on. And for ping, we want to conditionally call ping. So I'll say if x is greater than 0, I think that's the right way around, then we'll call ping with 1 minus x. Otherwise, we'll do display. Actually, we can just return x, can't we? That appears correct. So now if we try and run that again, I think this will Stack Overflow because we haven't yet implemented. Oh no. Tail calling. In an if expression. Is this the wrong way around? It's the wrong way around, isn't it? No. What is going right here? I was totally expecting this to explode. So ping passes on the argument. Pong takes the argument and that is way too big a number for this to. Let's just solve this by saying we just always call ping. Okay. If 0 is greater than x, that's always going to be it's going to be false until x goes below 0, and then we return x. Missing, closing. That is like that. How is that completing? I'm tempted to debug this. Let's run and debug. It's going to be spec bin tail. Oh, I need to actually build it first. And we'll do configuration debug as well. So configuration debug in our compiler doesn't change the IL we emit or do any. Oh, the what have we done there? Wrong. Oh, I put it in the wrong place. We want that to be there rather than in between two other arguments. So now let's try running it. Spec bin tail.dll. So ping, right? Okay. Ping should call pong, which it does. Then where do we go? We go to the call to ping because X is big and 0 is not bigger than it. So we take what's a step, and then we go to pong. What's X now? It's 999. Okay. And then that goes in there. Yeah. Well, that was silly. So this wants to be minus x1. And then I think we should be good. I think this should fail. Nice. So what that's proving is that this is not tail recursive because it's in an if. So what we need to do is have a think about how we're going to implement tail recursion in ifs. So let's go find the if. It's bound syntax. If. Yeah. No. Let's go right. I know it's in the meta expression. So here we go. Error sequence point store if. So we know that we can't tail recurse into the condition, which is fine. But down here, we want the if true and if false to be able to be tail recursive. Now, if we remember back to the IL that .NET is expecting, .NET is expecting to be able to see something like IL whatever, and then it's expecting to see tail dot IL. Then it expects to see call, or call vert in our case, which we do for func object array object. I mean, that's and then it's expecting to see a ret instruction. So the problem we have here is that this is what we're expecting for tail calls, but our ifs are lowered like IL, we do first, we do the expression. So there's something on the stack. Then we do duplicate isInst and branch if false. So we do effectively, we can ignore this isInst stuff and the pop down here, but we want to effectively do we go to is it's true, either if it's bool or not. Both of them are effectively just a branch. So we do br true il ddd, then we have il c, which is going to be false expression, and then true expression. What's happening here though is we do a br, an unconditional branch, to past here, well, we've put a not. So our ifs basically start by doing the condition. If it's true, branching to here, doing whatever the true expression was supposed to be, and then not. And if it was false, they fall through, evaluate the false expression, and then do an unconditional branch through to the same not. The problem with that is that in neither of these cases is the false expression nor the true expression followed by a ret. So we can't just say, oh, well, if your false expression ends in a call, we can just do a tail.call. Because if we do that, the .NET compiler will complain that our program is invalid. So I can prove that by just changing this to be tail. So if I pass the tail call flag on just like this, this should fail in a new and different way, which is it should raise an invalid program exception because it will have identified the fact that the call is in a tail position and it will do a tail.call. There you go. Common language runtime detected an invalid program. But we're close. So we know that we're correctly emitting tail if either the true or the false was in a tail position. What we need to do is not be doing this branch. So what we can say is, where would these branches be going to? So we know that if we're in a tail expression, the thing we're expecting to see next is a ret. So what we can just do is say, if we're in a tail context, instead of doing a branch, just do a ret. And then if we're not doing this branch, we don't need this not, which means that we can then just go straight to the ret. So to do that, what we would do is up here we say if tail codes.ret. So if we're in a tail position and then we'll just return straight away because we can fast track because this jump is only going to take us to a return instruction. And then we do our standard false stuff, and then down here we can just say if tail, no, sorry, if not tail. So if we aren't in a tail context, then we need this branch target. If we are in the tail context, we won't have ever used the branch target, so we're fine. We don't need to omit it. And then this should hopefully work. So that's running. Is it ever going to complete? How big of a number did I ask it to count down from? Maybe too big of a number. Let's go back to 100,000. So we don't have to wait for so long. Boom. And just to prove, I guess, that is dependent on the tail, we can set that to false again. Rerun and hopefully see a stack overflow. Yeah, And then I think we've already got a recurse up here which passes tail on, so we can change this to just be recurse and recurse. And that's it. We probably want to put a comment here to say what we're doing. If we are we can take this example here. To LBL end will be and then we could say we only need branch target if and then let's take this and move it somewhere up here and say so this is actually going to be LBL true, so we'll just use actual names here. So we'll call that IL LBL true, which is going to be this one. That's going to be LBL end. Just align these. So the false expression and true. We also have the LBL not bool. So we actually do an expression for cond. Then we do so if it's not a boolean, we do that here. Oh, no. And can I remember what it is to do multiple cursors? Yes. And so we want to annotate this with what we're doing different. And then here we say, instead of branching to for standard, yep, I think that explains it. So I think tail should now let's do this so that we get some output. So we say, instead of in the non-tail recursive case, we say without tail, proper tail recursion, this will overflow the stack. Or with proper tail. And let's move that right up to the top. For some reason we aren't getting proper Git support in Visual Studio. So what do we want to do? So let's remove that tail directory, which is our example, and let's run the tests. So I'm expecting the tests should all run, but we'll end up with a failure here because we haven't yet generated the snapshot for the tail recursive test case. Two failures. And yep, a snapshot does not exist. And a snapshot does not exist. Both of them are for tail.scm. So if we run the update snapshots, we should get a clean test run. I think that's it. I think that is tail recursion implemented. So I don't quite know what's going wrong here. Ah, there we go. So we have tail.scm staged. We've got the changes to our compiler. We'll go through those in a second. We've got the two snapshots. So the output of there is -1 because we decremented it until it was below 0. And then, but there are no errors. And we've got the pass, so we'll just stage those. So the changes that we've made to the compiler, we've got this new parameter tail to emit expression. We pass it on when we're in a sequence and application. We've made this change to the if so that we always pass on false for the condition and then recurse for the true and the false cases, conditionally either returning if it's in a tail context so that we don't end up with bad IL. For sequences, if there's one item in the sequence, we pass on the tail context. If there is more than one, as in, well, if we aren't the last one, we always set it to false, so we never generate tail calls unless we're the last one in the sequence. For applications, when we're generating the applicant and the arguments, we don't pass on the tail call because we can't tail call in those places. And then if we are in a tail context, we emit the tail prefix on our codes. And then the actual root, when we're emitting the body for a lambda, we call emit expression with true. So the body of a lambda is considered as a tail context. Support, well, that's an odd way of spelling support. Let's say it doesn't implement initial implementation of R7S 3.5. This adds tail. Post-production will here. So the stream dropped at this point. I was just staging changes and then I'll continue on from where I started discussing how we should implement tail call support in some of our macros. Spec has to say about proper tail calls. It'd be interesting to find out whether or not our and or macros support tail calls, but begin does, because our begin just produces a sequence expression. We don't support do's yet, and I think all of our lets should work correctly because all of the bindings that are done by lets happen higher up. That's done in bind expression, I think, and we're only working on the actual lowered values. Let yeah, so we do a bind let and they produce like a series of stores. So yeah, we just end up with a sequence, and we already support sequences, so that should all work. And when and unless we don't have support for yet. So it's just a case of what happens in and or. So and our and macro it's just called like macro and or something. Yeah. Our macro and will just expand to a sequence of ifs. So that should work. And the or turns into a let binding. So again, that should work. How can we prove that? We can, for the tail, we can do something like this. Let's say, actually, let's define it all at the top level. No, let's do it like this. So we say let foo be a lambda and it's just going to be and if it's true and then the second. So what was it saying? The spec said that the right hand side of an and or the last expression in an and should be tail and the last expression in an or should be tail. So we can do an or here, which should still be in tail, and then we say false and then boo. And then we can do an if here. So make this take a parameter 100 and say we'll do that wants to be an identifier, so we say x, then we say if greater than 0 x, then we return true. Otherwise, we'll do a recursive called foo with x minus 1. And that should be, that should print out true. Let's go find a bash terminal again. That's the right one. Missing closing. We've not closed off the display. So that also wants to have. So foo is the lambda, which has the and that. And then that's closing the foo declaration. That's closing the let bindings. That's calling the function, closing the let overall, closing the display. And then that should work. Nope. This needs to be a let rec. Otherwise, the binding won't be in scope. Expected system.double, but found system.boolean. arithmetic greater than. What on earth's happening there? So it's lambda 2, which is this lambda here. This is awkward. What is going on? So we've got is that the problem? Let's do just no build here just so that we speed things up a little bit. Expected system double but found system boolean. So it's this. If it's kind of implying that X is a boolean. Can we say display X? It's minus a lot. Oh no, there's no new line. It's 10,000. And then this is saying, so if we do this, is it this arithmetic greater than? That's complaining about. False. It's going to be somewhere in here, I guess. Is it the and? These both look correct. I must somehow or other be... Let's try taking them apart one by one. So let's do the and first, because that looks simpler. So, so the and there, the or there, then we've got the if. Let's move the if inside. We can just do the recursive call. It's fairly confident that it's not the recursive call that's problem. So if I remove the and the or, that should be pretty close to what we had before. And that was working. So we got a bunch of falses and then a true. So if I add the and in, so an and of a true and something, we don't need to display that there, I don't think. Let's just comment that out. So it's if we do an or, and so that's because the or is being turned into expression one, expressions, if not condition. Oh, that's unless, sorry. Macro or if, and then two. It's going to do a let. Oh, damn it. It's macro hygiene. Macro hygiene fine. I've got an idea for this. How about we use the finest of GUIDs, by which I mean one that was just generated by me. In that let binding. And now yes, we need to rebuild the compiler now because we've just changed what's in the built-ins. So we can get rid of the no build flag. Okay. And let's update the snapshots then for this. Let's run all the tests then, just to make sure that we haven't broken something else, because it could well be that that bit of a hack there with the built-ins has ended up breaking things. Now, 2 fails, which hopefully are going to be spec fails. Snapshot, yeah, now it's expecting, now it's getting that, and the pass should be different as well. And then we say that flow into and or macros. That's let's try and indent this a little bit better. So never 100% sure what the style is with Lisp indentations. I think it quite often can just be whatever you want. Whatever makes the most sense. So that's our definitions block, and then this wants to be there, like that, I think. So let's update the snapshots. And our new test change to the built-ins. Is that the only place that we've used a let? I think it is. This only works for one level of OR nesting as well, which is, I think, which is no, I'll work for any level of OR nesting, but because we just define it and then immediately return it, and then if you'd got if either one of these was nested, it would have already overwritten it here, and then we would have reassigned it. Like if test 1 was an OR, it would have written to what was X, what's now this GUID, and then we'll overwrite it and then check it and then return it. I mean, what you're supposed to do is rename symbols in macro expansion properly to get proper hygiene, but that's just a backlog issue. Should we split this into 2 things? We could split this into 2 things, couldn't we? And then fudge. Or adds test for tail recursion in macros. And I'm seeing some Git errors. What is it upset about? That is what it's complaining about. Unless GitHub's down or something. I don't know. Anyway, I think that's it for this stream. So I'm going to wrap up here, and hopefully in the next stream we can start taking a look at implementing scheme libraries. So the scheme specification talks about program structure. So programs are not 100% dealt with properly in our current compiler. What they're saying is that programs should be effectively a list of imports followed by a list of definitions followed by a list of like expressions. And one of the things that you can define is a library. So we don't yet support importing because we don't have any idea of namespaces and libraries. So we'd have to add supports for that. So what do we compile a library to? How do we import stuff from them? And then we'd have to add support for the define library form. So that looks like define library. So a define library is an example. This defines a library called example grid. It says what it imports, what it exports, and then it has a begin block, and you can have more than one begin block where you basically include bits of code that are evaluated when the library is loaded, and they can define symbols that you can then export, and then you can have various different parts of your scheme program depending on each other in a kind of nicely encapsulated way. So I think that's going to be the start of a series of different streams to get that working. I think the next stream will probably be having a look at the implementing import declarations and exporting our current built-ins, which we have in our Shrifa project. So things like the char methods and list methods and stuff like that. So these are all, according to the specification, defined in libraries. So you can import things like scheme base and scheme, I don't know if it's scheme list, but yeah, various different libraries. So we will have a way of marking up our built-ins as belonging to libraries, a way of modeling those namespaces in the compiler, and then a way of importing them. But that's it for today, and thank you for watching. I'll see you next stream.